In this video, we're computing a definite integral of cosine 2 pi x dx. And the limits of integration here are -2 to 2. Now there are two very distinct ways of doing this integral, and the more sophisticated method is to really think about the geometry that's going on here for this function. I'm going to take the geometric approach to the integral first, and then we can follow that up by taking a more formal algebraic approach, and we'll see that the two answers agree. So the key to this geometric approach is to think about the periodicity of this cosine function. The period of this function is 2 pi divided by the coefficient of x in that argument. And the coefficient of x is 2 pi, so I end up with a period of 1. Then I realized that I'm looking at a sinusoidal function, the cosine function, going through an integer number of periods. It goes through exactly 4 periods on this integration interval. That means it's going to spend exactly half its time above the x-axis and half its time below, and the integral should vanish. And to really be convinced that this works, we need to look at a picture of the function. So there's our cosine function going through exactly 1, 2, 3, and 4 periods. And there's more than one way to see that all the areas cancel out, but if I just look at the first period that I see in the graph for this cosine function, there's a positive half of a bump right there, and then I end up with a negative entire bump, and then another positive half of a bump. That's the completion of the first period in the picture. And I can see the signed area comes out to 0 there. So all I do is repeat that for the second period, the third period, and the fourth period, and I'm convinced that my signed area comes out to 0. So when I teach a calculus class, I actually consider this to be the superior solution to the problem because we've used some deep geometric insight to bypass any need for algebra. As long as the explanation is thorough enough, this is considered the better solution. I know that my original integral vanishes because this sinusoidal function completes an integer number of periods on the integration interval. Now, of course, you can grind through this with an algebraic approach. And even for this algebraic approach, there are multiple ways of going at it. I strongly encourage my students to avoid an explicit u substitution if they can see the chain rule backwards. And what I mean by this is if I just pop a factor of 2 pi into the integrand, I can see that I have the derivative of the interior function sitting right next to this cosine piece. And of course, I can't just go around putting factors of 2 pi wherever I want. So I have to put a 1 over 2 pi out in front. And I recognize the integrand now as the result of the chain rule operating on the sine of 2 pi x. So I get a 1 over 2 pi sine of 2 pi x evaluated from -2 to 2. And the key to getting comfortable with using the chain rule backwards is to just check your answers all the time. The derivative of the sine of 2 pi x gives me the cosine of 2 pi x, because that's the derivative with respect to the argument of that function. The chain rule says now you have to tack on the derivative of 2 pi x, which we cleverly put into that integrand to make it easier to see. So now we just have to evaluate across the limits of integration, and I immediately see the answer comes out to 0, because I have in the upper limit a sine of 4 pi, and in the lower limit, a sine of -4 pi. Both of these terms are 0, and again my integral vanishes. So hopefully this video has made you somewhat more likely to look for this kind of symmetry in the future. This is a really handy thing in applied mathematics. Anytime you see a sinusoidal function integrated on an integer number of periods, you know you can just cross those terms out and then focus on the things that are non-trivial. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left. Or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.